Good evening, everyone. Today I will be talking about the NACA 2410 airfoil profile, lift and drag coefficients, and low Reynolds number. Let's begin with a brief introduction about the relevance of airfoil geometry and how the slightest variation, even though it might seem millimeters to us, it actually has a huge impact in two key aspects for an aircraft. For instance, the first one is through the ability that an aircraft can transform airflow into actual lift and how it can minimize the energy loss from drag forces. Now these two components are more easily observed with these two formulas right here for lift and drag forces, and as you can see, lift and drag coefficients not only help us to view the behavior of an aircraft but also to understand the exact forces that it's subjected to. Now a brief thesis statement. This project will focus on analyzing and comparing the numerical values that can be obtained from computational fluid dynamics, such as ANSYS Fluent, and set them against experimental values like Airfoiltoolbox. This in order to prove the impact that the software has on the way that we obtain data as engineers. Now, delving into the methodology, the first step is to generate the geometry itself. You can use any plotter you'd like. There you simply modify the number of points. I chose 200 for a better accuracy. And you close the trailing edge in order to prevent any issues with the surface. And finally you set the chord length and any other parameters you choose to modify. I chose a 1 meter chord length to make it easier to manage. And then I draw the minion or the domain for the airfoil. This is 15 times the chord length, so 15 meters. As you can see, right here I drew two additional lines, one in the trailing edge, one is 80 millimeters offset from the leading edge. These two will help us to divide into 6 individual faces that have their individual meshing, and this will provide better and more accurate results. Now for the meshing itself, instead of using conventional element sizing, I chose to use a number of divisions, a bias type, and a bias factor. Now the number of divisions ranges between 150 to 300 divisions depending on the face. Then the bias type is the very first bias type, and a 300 bias factor for everyone. Now if you take a look at the meshing, you can see the domain is very finely meshed. You can't really see the airfoil, which is why I made a zoom over here. And even when you can see clearly the airfoil, you cannot see each of the number of divisions. So I zoomed in even further, and now you can see that the first division is smaller in size than the actual boundary layer of the airfoil. Now, delving into our solution method, ANSYS Fluent solves the project with RANS, which is Reynolds Average Navier-Stokes, then FEM, which is finite element method analysis, and finally I chose a viscous model, which was the SSTK omega, which is shear stress transport. Now the parameters themselves, I chose a Reynolds number of 500,000, and then this led me to my velocity of 7.828 meters per second, which is very common in low speed wind tunnels. Now my results, you can see I got two main graphs that plot the lift and drag coefficients against various angles of attack. I chose from 0 all the way to 17.5 degrees, mainly because it was an asymmetrical profile, and I focused my angles in this range because it was closer to the critical angle of attack. Now, when you think of critical angle of attack, it's important that you keep in mind stalling. Your aircraft stops producing lift, it's an erratic behavior, and then eventually it plummets. As you can see very clearly, the lift coefficient is going steadily up, and then it reaches the critical angle of attack of 15, and then it begins to fall. And the drag coefficient is steady up until the 15-degree angle, and then it grows exponentially. Now, you can also see the pressure and velocity contours at 0 degrees, which means that the fluid is perfectly horizontal to the airfoil. And here in the pressure contour, you can see the simulation is doing what it needs to be doing. there's a higher pressure below, a lower pressure above, which actually means that the lift is occurring with a sort of suction phenomenon, and then there's a higher pressure in the leading and trailing edges. Now, with the 0 degree velocity contour, you can actually see that it's a very linear behavior, and you can observe, if you go closer, the nose-lip condition, where velocity tends to 0 the closer it gets to the edge of the airfoil. Now, for an angle of attack of 17.5, this is past the critical angle of attack, and this means that the air has an inclination, which is why you can see that the airflow is going upwards. But not only that, you can also see that there's air recirculation, there's vorticity, and there's the cause of the erratic behavior I was mentioning before. So, if we move on to the discussions and my conclusions, you can see that not only the behavior of both graphs is very similar, but if you go into each individual numerical value, you can see that actually they're very, very close, as evidenced by my percentage error calculator. Now the lift coefficient has a percentage error of around 6.15%, and the drag coefficient is almost 15, it's 14.96%. Now this is because of the erratic behavior and the difficulty for simulations to actually predict or converge into critical values, but this can very easily be narrowed down, made more accurate by simply making a mesh-independent study, by adding more parameters, by making more boundary conditions, and overall making a more complex situation. This leads me to my conclusion, where CFD is only limited by two main factors. This is your computational power and your actual knowledge of how to conduct simulations. But being perfectly frank, your knowledge of simulations is no longer limited by if you have classes or not. There's a huge array of videos explaining how to perform simulations just like this one, more complex even, and not only for fluids, but for a various range of different experiments. Now, conventional experimental procedures can be quite expensive. They can be difficult to schedule even if you're a student and you can use them in your laboratory, and you have human error, and you have to have knowledge of the equipment itself. This was it from my end. These are my references, and I thank you all for your attention.